So typically S is going to look like this. So outside of some little interval or something, maybe S is positive just for the first few terms or something. Or just one term like we had before. So basically that's really not going to be there for most xt's. So you see you get a drift of rate 1. The conditional mean one step in the future is one less than where it was, where it is now. All right, so that's sort of the way of thinking about this in terms of expected drift and all of that. But let's go and monkey around with our friend here and show we can get bounds on this and all of that. First use first use the fact that S and nu have non-negative entries. So if I subtract off this S cross nu, I'm going to get something less than equal to PV. All right. So I don't really care about P. What I really would care about is this deviation thing, because that's the thing that's showing up in my thing that represents the invariant probability mass function. Right? And then we iterate this thing. So instead of just jumping to an inverse, because that's weird, let's just basically do the inductive argument that I've been alluding to before. Basically hit this again by P, or P tilde. Maybe we should give it a name. I know you all don't like me changing my notation, but we don't have a 1 and a pi now, so I'll call that P tilde. All right, so I've got an inequality. P tilde is a matrix with non-negative entries, so it preserves the inequality. If I hit both sides of this inequality with P tilde, I'm using the minorization. This difference matrix is a big giant matrix with non-negative entries. So I'm not going to, the inequality is preserved. So I can do that. Right, so I just multiply both sides of this functional equation by P tilde. And then I've got P tilde V, which I can go ahead and substitute in again. And I can do this over and over again, and also, very importantly, that's greater equal to 0. So does this look familiar? I mean, this is when I first introduced sort of Lyapunov functions, I did this sort of inductive thing before. I'm just doing something more refined now, because I've got this deviation term. Okay? So from here to here, I just hit both sides by P tilde. This is just a functional equation. V is a function in the state space, P tilde V is a new function. And so I can hit both sides and get that. And you can see where I'm going to go now. I can do it again and again and again. And every time if I hit it by P tilde again, I'm going to get a P tilde squared here. And then over and over again. So that's okay. This can die. So what you finally get is that 0 is less than equal to P tilde to the NV, less than equal to V, and then I get a sum of terms. I get a sum of the powers of P tilde times 1. Yeah. Yeah. And I'm going to let n go to infinity, right? So this is a thing that I said, oops, I forgot to say, that when I hit z times s, it gets something less than 1. So the partial sum is less than the full sum because these are all non-negative. So just instead of taking n here, just go to infinity, I get an inequality. All right? And I told you I could prove by induction that zs, which I just called h, is less than equal to 1 everywhere. And I'm sorry, that is an inductive proof. It's algebraic, it's not a big deal. So I'm just, that's the only thing, there's an inductive argument I'm leaving out of this lecture. And it's just, I could just squeeze this into 2 hours. Okay, if anybody's curious, I'll send you a reference. All right? All right, the fact that zs is always less than equal to 1 everywhere. And then so now I've got a uniform bound that's true for every n. And so I can let n go to infinity. And so the sum from 0 to infinity 1 is less than that. Right? And so what I get is that nu z1 so remember mu is nu times z. So the thing I was interested in was mu. Is it finite or not? All right. Well, the sum over all x of mu of x is just the dot product of mu and 1. And mu was nu times z. So this mu times 1 is nu times z times 1. And that's less than equal to nu times v plus b. And I'll use that, you know. I mean, nu of v is a dot product. I mean, I could write nu v if you like. I mean, same thing. Nu of v is a dot product. So where's the gap, everybody? I was trying to show that mu is finite. Have I showed mu is finite? What's one gap is that why is that finite? But it comes down to here. I hit both sides of this by v, and I get a nu of v over here. And that's less than p times v. I mean, PV for any x over S of x. It's finite. I mean, in order to show this is finite, I take this outer product times v, and the outer product is less than or equal to p. We just said that. And pv is less than v minus 1 plus blah, 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 blah. That's finite. Whenever s is positive, I can just divide, and I get nu v is less than the ratio. So this is finite. So QED, so mu of x is finite. All right, so that's it. That's what Foster proved using very, very different methods, okay? And just really quickly, I'm not going to give a proof, but I want you to think about it. So you look at my book with Tweety, there's something called V3, where you take the same thing. This is what we've talked about already. This is a case where there's like f is like bounds a cost function you care about. You know, it might be a quadratic. In queuing systems, like we mentioned, we take it to be linear. That's the kind of thing we care about. And we solved this, basically, for the queuing model. And what's going to happen? Instead of a 1 here, I'll have an f. All right? So when you see p tilde 1, you'll have a p tilde f. So you go through the same proof, just replace 1 by f everywhere you go. And you find that mu of f is finite. And then if you look at my book with Tweety, and I'll send you out some notes, this looks just like this, but with f is a scaled version of v. Okay? And this turns out to be equivalent to, well, of course, mu of v is finite, because it's basically the same sort of thing. But this is equivalent to geometric ergodicity. So if it's aperiodic, and I'm going to have to talk about the graphical sense, because eigenvalues of a countable state space matrix, you know, it's too confusing. So just in the graphical sense, so you don't have this decomposition. Then probability n steps of going from x to x prime goes to pi of x prime at a geometric rate. And what's really crazy is how easy this is to prove. I won't do it, I promise. But you wouldn't believe how fast it is to prove. It is like unbelievable how simple this ergodic theorem is. It's just, it's almost as simple as what happens in the finite space case we talked about last week. It's almost that easy. You know, you need a little bit of linear algebra. And I know half of you aren't that comfortable with linear algebra, so I won't do it. But this is equivalent to this. So you get geometric convergence to steady state if and only if there's a Lyapunov function like this. And the proof is that it would take me 20 minutes if you had the right linear algebra background. You know, so this is anybody that wants the reference, I can send it to you. But these people are obsessed with these Lyapunov functions, not so much because they're obsessed with countable state space or general state space Markov chains. I mean, some people are, but you get bounds. I mean, this is a really crude bound. You can get much better bounds than that. You know? And people are interested in rates of convergence of Markov chains to stationarity. They're interested in that for simulation. Well, you can get rates from this. Maybe not great bounds, but you can get rates of convergence from this. And people really care about that. You know, basically in statistics, it's an obsession to get a rate of convergence here. Absolute obsession. And we might come back to that. Like in Markov chain Monte Carlo methods, that's the gold standard, is to get some bound on a rate of convergence here. All right. Oh, damn. I do talk fast. All right, so really it was just a bunch of linear algebra and practicing notation. It really was. There wasn't a lot of content here. The next steps are really not that much. You know, I want to give a little more background to get us ready for looking at hidden Markov models and state estimation and all that. and maybe a little bit of limit theory, but just briefly. So I think just a couple more hours of Markov chains, which means we're moving ahead, which is awesome. It means we'll be able to slow down during the statistics part, which can be pretty scary. So which is nice. But I guess that's it. So it's time for office hours. So cameras out. Let's get to it.